What if the AI that, just flawlessly booked your flight, managed your calendar, and coded your website actually has no idea how the real world works?
Right, it sounds totally counterintuitive.
It really does. I mean, we have this lingering assumption about highly capable systems, like a pilot flying a commercial jet. You'd expect them to know how to take off, how to land, the aerodynamics of a stall, and how to read every single gauge in that cockpit,
Yeah,
right?
exactly. We assume that high-level competence naturally requires an unbroken, comprehensive understanding of the environment.
Yeah, we project that human standard of universal mastery right onto machines.
We really do. We assume that if an autonomous agent can perform this 10-step, highly complex reasoning task, well, it simply must possess a complete and accurate internal model of the universe it's operating in.
But then you step into the actual underlying architecture of modern generative AI and autonomous agents, and suddenly that expectation just shatters completely.
It shatters into pieces, literally.
Right. We are looking at a landscape where expecting an AI to know everything is not just unrealistic, it's actually mathematically impossible. So, welcome to today's deep dive.
So glad to be here.
We have a really fascinating stack of sources to go through today, and they are anchored by a foundational state-of-the-art research paper. It's called World Models in Pieces: Structural Certification for General Agents.
It's a fantastic paper.
And for anyone listening who is wondering how we can actually trust AI to perform complex tasks without going totally rogue or hallucinating mid-task, well, this deep dive holds the key.
Yeah, the authors of this paper are fundamentally redefining what makes an AI general.
Because the industry has spent years chasing this, fantasy of an omniscient machine, right?
Exactly, and this research forces us to abandon that entirely. We have to look at how real mathematical trust is built in these spaces where an AI's knowledge is profoundly fragmented.
Fragmented how? Like missing pieces.
Basically, yes, we are dealing with models that have these specific chunks of high-definition clarity, but they're surrounded by total static everywhere else.
Wow, okay. So my mission today is to take the heavy math in this stack of research and translate it into a massive aha moment for you about AI safety and reliability.
It's so crucial for anyone working with these models.
Because before we can deploy these agents into the wild, we really have to understand why our current expectations are setting us up for catastrophic failures.
Right.
So let's unpack the core problem here. The authors start by introducing what they call the big world hypothesis.
Yes, the big world hypothesis. So in a truly complex environment like the internet or a physical city, the space of all possible long-horizon goals is just exponentially larger than what any bounded agent could ever explore.
Bounded meaning limited, right?
Exactly. An AI has limited memory, it has limited compute, and limited training data. It simply cannot map the entire state space of reality. It's too big.
So, because the environment is just too vast, the researchers introduce Proposition 3.1. And I read through the proof for this, and it's essentially the mathematical nail in the coffin for the idea of a universal AI, isn't it?
It really is. Proposition 3.1 mathematically proves that a universal agent cannot exist.
Wait, cannot exist at all.
Right. Specifically, it proves you cannot have an agent capable of maintaining a uniform failure rate over the entire goal space when the tasks have arbitrarily large depths.
Okay, let's unpack that a bit for the listeners. What does that mean in plain English?
Well, look at the mechanism of compounding error.
Mm-hmm.
If you give an AI a multi-step task, say a sequence of 100 actions,
Okay, 100 steps.
and it has even a microscopic margin of error at every single step, those errors don't just add up, they multiply.
Oh, right, exponential growth.
Exactly. So in an impossibly vast environment, the probability that the AI eventually wanders into a state it fundamentally misunderstands approaches absolute certainty.
So the uniform guarantee just collapses under the weight of exponential complexity.
Precisely. You just can't boundedly guarantee success across a universal set of goals.
Expecting an AI to be universally optimal like that, with a uniform failure rate, it's like expecting a human to be an Olympic gymnast, a quantum physicist, and a master chef all at once.
Yes, all at the same time.
And not just pretty good at them, but world class, with the exact same tiny margin of error across the board, no matter how weird or novel the situation gets. It just doesn't happen.
The math dictates that any bounded agent's policy will inevitably have blind spots. If the sequence of tasks is long enough, what the paper actually refers to as the goal depth, the AI will eventually hit one of those blind spots and just fail.
But wait, I have to push back on the terminology here for a second.
Sure, go ahead.
We call them general agents for a reason, right? The whole tech industry revolves around building artificial general intelligence right now.
True.
So if the math proves they aren't universally capable, what exactly are they? Why are we still using the word general?
It's a great question. The term general is a bit of a historical misnomer, honestly. And the paper addresses this directly, which is actually the crux of the title: World Models in Pieces.
Oh, I see.
The authors clarify that general agents are actually highly capable specialists on a subset of goals.
Highly capable
Yeah,
specialists.
their capabilities are inevitably uneven and intensely localized to specific transitions in the environment.
So a general agent might be incredibly reliable at a specific set of tasks, but utterly clueless about another set.
Exactly. And this gap might remain completely unnoticed until you ask it to execute a long horizon plan that forces it to cross through the territory it doesn't actually understand.
Which forces a total paradigm shift in how we evaluate these models, doesn't it?
It absolutely does.
Because standard worst-case analysis, where you judge an AI by its absolute weakest link across the entire universe of tasks, that becomes a completely useless metric.
Right, because under that lens, every single AI fails.
Because Proposition 3.1 guarantees a weak link exists somewhere.
Exactly. Evaluating an AI based on universal competence is literally evaluating it against a mathematical impossibility.
Okay, so this brings up an obvious logical contradiction.
What's that?
Well, if the AI's internal knowledge of the world is just a bunch of fragmented pieces, how does it ever manage to successfully complete complex, long-horizon tasks?
Ah, right.
I mean, we see AI agents today successfully scraping the web, booking flights, synthesizing huge amounts of data. How are they succeeding in reality if their underlying world model is so patchy?
Well, success in realistic tasks doesn't actually require knowing the whole world. It relies entirely on mastering what the authors identify as decision-critical bottleneck transitions.
Bottleneck transitions. Okay, let's break down the mechanics of a bottleneck transition.
Sure. Consider the realistic web tasks mentioned in the sources. So, logging into a website, selecting the correct item variant on a complex store page, or successfully submitting a checkout form.
Standard AI assistant stuff.
Right. In the massive, dynamically changing environment of the internet, overall success for a shopping agent hinges entirely on these single high-leverage steps.
Because the web is just full of noise.
Exactly. The mechanics of the web might involve millions of irrelevant variables. Ad trackers loading, background videos playing, CSS elements shifting around on the page.
But none of that matters for the task.
None of it. If the agent successfully inputs the credit card and hits submit, it wins.
So inaccuracies in the agent's world model regarding all those irrelevant background dynamics, they simply do not degrade its performance.
Not at all. The agent's policy is only querying its internal world model along the specific trajectory required to click that checkout button.
I picture this kind of like navigating your daily commute to work.
Oh, that's a good analogy.
You don't need to know the aerodynamic engineering of your car, right? And you definitely don't need to know the exact molecular makeup of the asphalt you're driving on.
No, of course not.
You literally just need to know how to merge onto the highway and take the correct exit.
Yeah, precisely.
If your mental model of how the engine combusts fuel is completely wrong, like maybe you think tiny hamsters are spinning wheels under the hood, it doesn't stop you from getting to the office.
That's hilarious, but yeah, exactly. That knowledge isn't a bottleneck for the task of steering the vehicle.
It's just irrelevant.
And the mathematics in the paper back that analogy up beautifully. An agent interacts with the world in pieces. It frequently succeeds despite having a completely wrong causal model of irrelevant dynamics.
As long as it gets the bottleneck right.
Exactly, provided it has an accurate causal model of the specific transitions required to pass through that bottleneck.
Okay, so the math says this works in theory, but how do you actually force an AI to prove it understands these bottlenecks in a real, observable environment?
That is the big question.
Right, because if it's succeeding, but its overall model of the world is mostly wrong, how do we know we can actually trust it? Knowing that AIs rely on bottlenecks is interesting, but how do we mathematically prove they understand the bottleneck they're passing through and aren't just, getting lucky?
Well, the paper introduces its main theoretical contribution to solve exactly this problem. It's called structural certification.
Structural certification. Let's break down the mechanics of that for the listeners.
So instead of relying on universal worst-case guarantees, which we know are impossible, the authors introduce a framework to mathematically isolate specific localized transitions.
How do they isolate them?
They achieve this using prod goals structured with linear temporal logic, or LTL for short.
Linear temporal logic. How does that actually work in practice to isolate a transition?
Think of LTL like an incredibly strict, multi-stage obstacle course for the AI's logic.
Okay, an obstacle course.
It's not just giving the AI a final destination and timing its run. It is placing highly specific conditional checkpoints in places where the AI will only succeed if its fundamental understanding of cause and effect is correct.
Oh, interesting. So it's not just go from A to B.
Right. Instead of a simple prompt like, go to the end, LTL allows researchers to program a probe goal like, first, take action A until you reach state B, then eventually reach state C, but only if you did not pass through state D.
Oh, wow. So by giving it these highly compositional goals, you basically force the AI to repeatedly navigate the exact bottleneck transition you want to test.
Yes.
And from multiple different angles and starting conditions, too.
Exactly. You are essentially cornering the agent's logic. You are forcing its internal world model to expose its underlying mechanics.
Here is where I have to challenge this whole complex certification process, though.
Okay, let's hear it.
I was reading Theorem 3.3 in the text, and it made me question why we need LTL or probe goals at all.
Oh, Theorem 3.3 is huge.
Right, because in the real world, if I watch an AI successfully navigate a web store checkout 100 times in a row, why can't I just assume it knows what it's doing? Why can't we just rely on observing a highly successful behavioral policy?
Theorem 3.3 is perhaps the most crucial warning in the entire paper. It mathematically proves that merely observing an agent's policy, just watching it succeed over and over, is completely insufficient to guarantee it actually understands the world.
Even after 100 successful attempts?
Even then, the number of successes doesn't matter if the underlying mechanism is fundamentally flawed.
Wow.
Theorem 3.3 states that any policy-only behavior rationalizing algorithm can be fundamentally fooled.
Fooled how?
Well, without external verification using probe goals, an AI might just be relying on a fragile heuristic, like a spurious correlation it picked up during training.
Give me an example of how a behavior rationalizing algorithm gets fooled in reality.
Okay, imagine an AI trained to check out of an online store. During training, every single submit order button it happened to see was green.
Okay, green buttons.
The AI might build an internal world model that says clicking any green box results in a successful purchase.
I see where this is going.
Right, so when you observe it testing on similar sites, it clicks the green button, the order goes through, and it looks like a genius. It rationalizes its behavior perfectly.
But it's doing the right thing for entirely the wrong reasons. It doesn't actually understand the causal mechanism of a checkout form. It just likes green boxes.
Exactly. And the moment the environment shifts slightly, say a website uses a blue checkout button or puts a green advertisement next to the cart, the agent fails catastrophically.
Because its underlying model of reality was always mismatched.
Yes, it was just hidden behind a streak of coincidental successes. You can mathematically construct a fake world model that perfectly explains the AI's successful behavior in a narrow set of observations, but differs fundamentally from the true dynamics of the real world.
So just observing behavior is a massive trap.
It's a huge trap. Structural certification fixes this by forcing the agent to navigate conflicting probe goals.
The obstacle.
Right. The LTL obstacle course might force the AI to interact with green boxes that aren't checkout buttons, or checkout buttons that aren't green. By isolating the transition in this highly structured way, the algorithm anchors the agent's internal model to a known, verified transition probability.
So it strips away the heuristic and isolates the true causal mechanism.
Yes. If the agent passes the certification, you have mathematical proof that its predictive world model perfectly aligns with reality for that specific step.
And the researchers actually proved this mathematically with a new error bound, didn't they?
They did, and the leap in mathematical accuracy here is just staggering.
Let's get into the numbers.
Previous works in this field relied on universal guarantees, and their error bounds scaled at a rate of big O of 1 over the square root of n.
Okay, and for those not living and breathing complexity theory, big O notation is just a way to describe how the error scales as the task gets longer and harder.
Exactly.
So the old method had an error bound of big O of 1 over the square root of n.
Right, where n is the goal depth, meaning how many steps ahead the AI is planning. But this new structural certification provides a much tighter error bound of big O of 1 over n, plus an additional big O of delta term.
Okay, where delta is the localized failure rate, right?
Correct.
So why does testing localized bottlenecks mathematically cause the compounding error rate to drop from a square root to a linear fraction? What is the actual mechanism driving that massive improvement?
It's because we are no longer testing the AI's knowledge of the entire universe.
We shrink the testing pool.
Right. When you try to estimate an error bound across an expanding sequence of unknown states, the mathematical uncertainty compounds endlessly, which gives you that slow square root convergence.
Makes sense.
But with structural certification, we have strictly isolated a single action and reward loop. We've turned a massive open-ended problem into a highly localized estimation problem.
So because the transition is isolated, the variance shrinks much faster with repeated sampling.
Exactly. Pulling the error bound down to big O of 1 over n.
That makes perfect sense. And bounding the error that tightly is critical for multi-step reasoning, isn't it?
Absolutely essential.
Because if you have a loose error bound, an autonomous agent could start hallucinating wildly by step 50 because the mathematical uncertainty has just ballooned.
Yes, the compounding error takes over.
But with this linear bound, it stays on the rails.
Right. The extra big O of delta term simply quantifies the slight blurriness introduced if the AI isn't perfectly optimal within that specific bottleneck. But since we are only certifying high-performance transitions, delta is extremely small by definition.
The math works beautifully on paper, but how does this play out in a simulated environment? Because the researchers didn't just leave this on a chalkboard, right? They ran empirical validations.
They did.
Let's dig into the maze experiment.
So the authors set up a stochastic grid world to test this. It was a maze with 625 states, basically a 25 by 25 grid.
Okay.
And the agent had 5 possible actions: UP, down, left, right, and stay.
Let's define stochastic grid world really quickly for everyone. It means there is built-in randomness in the environment, right?
Yes, exactly.
Like if the agent tries to move UP, maybe a simulated gust of wind pushes it left to left 10% of the time.
Right, so it can't just memorize a fixed sequence of keystrokes. It actually has to understand cause and effect and navigate those probabilities.
Got it.
The grid also contained solid walls, which were represented by black cells. If the agent tried to move into a wall, it simply remained in its current cell.
Okay, pretty standard maze stuff.
Right. So the researchers trained these agents using random walks to build up an incomplete, fragmented empirical world model. Then they applied their structural certification algorithms to map out exactly which transitions in this maze were verified.
I picture this like sending an explorer into a massive pitch black labyrinth.
Ooh.
They don't have a map of the whole thing. They only have a flashlight that perfectly eliminates a few specific jagged paths they've managed to structurally certify.
That's a perfect way to visualize it.
But everywhere else, they are operating in total darkness.
So to test the flashlight, the researchers designed 2 specific compositional tasks.
What was the first one?
In the first task, they placed a key and a door inside the maze, but they deliberately placed them in transitions that had been successfully certified by their algorithm.
So the target was placed squarely in the path illuminated by the flashlight.
Exactly. Because those bottleneck transitions were certified, the agent's internal model was provably accurate there. It understood the stochastic mechanics of those specific tiles perfectly.
So what happened when they set it loose?
When tasked with finding the key and opening the door, the agent generated near-optimal stable trajectories. It navigated the probabilities, grabbed the key, and unlocked the door with incredible reliability.
Because it knew exactly what it was doing. Its world model for those specific pieces was rock solid.
Yes, but then came the second task.
Oh, boy.
The researchers took 2 different objects, a pen and a piece of paper, and placed them in transitions that had failed certification. Now, the agent had some behavioral data there, like maybe it had stumbled through those tiles during its random walk training. But its internal model hadn't been structurally certified for those spots.
So placing the target outside the beam of the flashlight, out in the uncertified darkness,
Yep.
what actually happened to the agent's behavior?
Complete behavioral collapse.
Really?
Yeah. When tasked with finding the pen and writing on the paper, the agent exhibited highly erratic behavior. It got stuck in local loops, moving back and forth uselessly, and it continuously collided with the walls.
Wow. Because it was operating on fragile heuristics?
Exactly.
It was trying to use a fragmented world model that didn't align with reality in those specific spots, even though it was the exact same agent that just flawlessly opened the door a minute ago.
It validates Theorem 3.3 perfectly.
Hmm.
Just because the agent succeeds in one complex task doesn't mean it has a generalized understanding of the whole maze.
Its capability is strictly bound to the certified pieces of its world model.
Totally bounded.
I know they tracked the numerical differences between the old baseline error bounds and this new structural certification. When you compare the actual data from the maze simulation, how big of a difference are we talking about?
Well, we look at what's called the tightness gap. That's the difference between the theoretical error bound and the actual observed error.
Okay, the tightness gap.
At a planning horizon of n equals 100 and a failure rate of 0.01, the old baseline bound wildly overestimated the error, resulting in a tightness gap of 5.31%.
5.31%.
But the new structural certification bound had a tightness gap of only 0.35%.
Wait, 0.35%. That is nearly a 15 times improvement in mathematical precision.
It's massive.
Ooh.
In a sensitive dynamical system, an error bound of 5% is practically useless. It's far too coarse.
Right.
At 5%, you cannot mathematically distinguish between an AI using a cheap, fragile heuristic and an AI exhibiting genuine mastery of a task.
At a 0.35%.
At 0.35%, you establish a rigid mathematical safety envelope, with extreme statistical confidence that the agent actually understands the causal mechanics of that transition.
So what does this all mean for you listening right now? I mean, if you are a developer, if you are implementing AI at work or building autonomous agents into an app, you really have to fundamentally shift how you evaluate these systems.
You really do.
You shouldn't be asking, is this AI universally smart? Or does this AI understand everything about the internet? That is just the wrong framework entirely.
Because you are chasing a mathematical impossibility that will inevitably lead to compounding errors.
Instead, you should ask, have we identified the critical bottlenecks for this specific task?
Yes, find the bottlenecks.
And more importantly, have we structurally certified the AI's understanding of those exact bottlenecks? If you can isolate the logic with probe goals and certify those specific transitions, you create that safe envelope for deployment. You don't need the AI to know everything. You just need mathematical proof that it deeply understands the few things that actually matter.
It's such a powerful framework for artificial agents, but it leaves us with a rather provocative question about ourselves, actually.
Oh, where are you going with this?
Well, this paper proves that highly capable AI doesn't have a universal model of the world, right? It is a fragmented model built around specific certified bottlenecks.
Right.
What if human expertise works the exact same way?
Oh, wow. That is an interesting thought.
I mean, we pride ourselves on having general human intelligence. We walk around feeling like we understand the whole world.
We do. We feel very competent.
But perhaps that feeling of universal competence is just an illusion. Perhaps what we consider general human intelligence is really just a well-connected network of highly certified personal bottleneck transitions.
Like, we deeply understand the specific routines and causal links that allow us to survive and succeed in our personal daily goals, our jobs, our commutes, our social circles.
Exactly. But outside of those certified pieces, in the uncertified darkness of our own personal maze, we might be just as prone to erratic behavior, false confidence, and fragile heuristics as the AI.
Are we all just operating on a series of certified bottlenecks? It makes so much sense, honestly.
It really does.
It explains why an expert in one field can sound completely unhinged when they start talking about a completely different field.
Yeah, they've stepped out of their certified safety envelope.
How about the flashlight beam? It
Yeah.
really humbles your perspective on both artificial and human intelligence.
It definitely does.
Well, that is all the time we have for today. Thank you so much for joining us on this deep dive. Keep questioning your bottlenecks, and we'll see you next time.